till now we have learned about refraction, about apparent depth, about real depth, and let's build on to that and think of a situation in which I'm thinking of refraction, but in such a way that this is a denser medium and this is a rarer medium. When I say denser or rarer, the easiest explanation is let this be 1 and this be mu, and your task is done. Let at this point I draw a normal. This is a normal. Now, if there's a ray of light incident over here, naturally, it won't go in this path. It would deviate away from the normal. Why? When a ray of light goes from a denser to rarer medium, it deviates away from the normal, which has been told a lot of times by now. And if I increase this angle further, how? We're passing a ray like this. My R, angle of refraction, would again be increased. Now this would be your new ray. Similarly, I can keep on increasing. I can keep on increasing my I, and my R would also keep on increasing. There would be a point when I increase my I to such an extent that my ray, refracted ray, is almost parallel to the interface. This is my interface. At which refraction is taking place. So there would be a particular value of I for which my refracted ray would be almost parallel to the interface. When it is almost parallel, your angle of refraction is almost equal to 90 degrees. And beyond that angle, refraction ceases. By which what I mean is, this angle, the angle at which your refraction angle of refraction becomes almost 90 degrees, is known as critical angle. And beyond critical angle, refraction ends. First, understand what exactly is the value of critical angle. Mu into sine IC is equal to 1 into sine 90 degrees. So your IC becomes simply equal to sine inverse of 1 by mu. Or in other words, in simpler words, your sine IC is equal to 1 by mu. Now, beyond IC, if I increase my I beyond IC, what will happen is there would be no refraction, which means, let's say this is your ray beyond IC. So it won't get refracted, it would be simply reflected along this path. So this is the particular ray which is suffering no refraction. This is a ray which is suffering no refraction. So I will say when this is satisfied, there is no refraction. Now, what do you mean by no refraction? There's a hint here in the word no and refraction. I have said to you that at every interface, two things takes place simultaneously. One, refraction, and the other, reflection. But over the period of study, we had assumed that initially we will think of only reflection, then think of refraction, and then combine them. So at this interface, both the things would take place ideally, practically, refraction as well as reflection. But if I is greater than IC, refraction completely ceases off, right? Which means only reflection is remaining. That is why this situation is also known as total internal reflection. The phrase itself explains you all that all the light totally is reflected back to the denser medium. It is not going to the rarer medium. It is abbreviated as EIR2. Now, only condition is I should be greater than critical angle. This is a critical angle. You can label this thing as critical angle. Now I have a good situation that for a particular situation, I'm not having refraction. So all the light is in this medium itself. Now this has a lot of applications. You can use this for making optical fibers and for having optical communication too. Why? Because if light is not suffering refraction, all the light energy is in this medium itself. So if I construct some kind of a situation, or rather construct a geometry depending on mu value, I can have a situation in which all the light ray entering a tube or a geometrical construction is getting total internal reflected, totally internal reflected, suffering TIR, which means all the energy is inside that tube, and this is used in a lot of surgical procedures. We use TIR for passing the light energy in a very focused way, and there's no loss of energy, so I can see the inside of your stomach or whatever body parts I want to see, internal body organs. Now this also has got application in communication systems. What I can do is I can put electronics signals on top of optical signals, or rather I can convert electronic signals in optical signals. I can pass on through optical fibers, and those optical fibers also constructed in such a way that all the signals are getting totally internal reflected. They're suffering TIR essentially, which means there's no loss of energy. Light is a form of energy, which means there would be a complete transfer of signal from this end to this end with just TIR taking place all throughout. Now this has also got application in few atmospheric phenomenon. Like you might have observed something called a mirage. Let's understand what a mirage is. On a hot sunny weather, what happens is the ground, or rather the road, gets heated up. If the road gets heated up, what will happen is this would be hotter surface and air above would be colder. And naturally, hotter air means less dense air, and colder air means high density of air, and mass density of air is somewhat related to optical density too. So this becomes your rare medium, or rather just rare medium, and this becomes dense medium. Which means as I go up, my density rises, optical density. I can just simply say my mu rises up. That would be sufficing my situation. The optical density is rising up. So I'll just say my mu is rising up. Mu is increasing. If mu is increasing as I go up, what would happen is, let's think of a situation in which I have an object like this. It could be a tree or a building, it could be anything. I made a very irregular shaped object because objects are of irregular shape naturally in real life. Now, if a ray of light comes from here, as it goes below, it finds rarer medium, which means it would bend away from the normal, which means it would gradually curve like this, because normal would be always in this way, vertically downward. So it would bend towards this. And at a particular point, what will happen is, this angle of incidence would reach critical angle. And after that, this ray would not suffer any refraction. It would simply suffer TIR, total internal reflection. And this ray would go like this. Right? And if this ray is going like this, what's happening over here is, if I'm observing this ray, I will think that this ray is coming from below. Obviously, this diagram is not proper. If I draw a proper scale diagram, what you'll see is that a similar height of thing would be forming below. But this would be inverted, and this is not the only thing which would be inverted. There would be a lot of other objects too, which would be inverted. And your eye again is a kind of a image processor, and it processes the image and learns from its history that what kind of object is that image of. And I cannot see water. My eye or brain cannot perceive water. But from learning about the world, what it understands is that if a lot of objects are inverted in a surrounding, this is because that surrounding is having water. Why? Because if you look at water, you would see reflection of a lot of objects, and all those reflections will be vertically inverted. So my eye and brain gradually learns and stores its memory that a lot of vertically inverted images means that it's a water body. Here also, a lot of objects would be vertically inverted. So my eye would just go back to that memory and bring it out and say that this is a water body. This region over here is a water body, which definitely is false. Why? Because this is a road, this is a surface, this is a ground. And the reason I'm thinking of this as a water body is because a lot of images are vertically inverted. And this kind of illusion is known as mirage. This is known as a type of optical illusion. And it is a combination of multitude of things. First is your total internal reflection. Second is the faulty image processing inside your eye. And the other factors of hotness decides the optical density of the air. So all these things decide that I would see an optical illusion as mirage or mirage, whatever the pronunciation you follow. Now, this is an application of TIR in atmosphere or atmospheric phenomena known as mirage or mirage, is because of this idea that a lot of images get inverted, and this kind of portrays to us that there's a water body over here, which actually there is no water body over here. This similar thing happens for ocean and river too. I mean, there's actually an ocean, but what actually happens, let's see. Let's say you are far away from a ship, and this is ocean surface. And as Earth is spherical in nature, so naturally, if ship is coming from far away position, it would be below you. Let's say this is ship. This diagram is not proper, just bear with it. Now, if you're standing over here, this is cold. Why? water has a very high specific heat capacity, which dictates that water surface would be cold and above it would be warm. So this would be your, and this one more assumption is taken care of, that this is only thought of for cold climate situations. Only then your water would be cold. Comparatively, a lot change in temperature would be happening between the air surface above and the water surface here. Now this is having higher mu, this is lower mu. So as the ray coming from ship proceeds up, it would find itself falling from optically dense medium, optically rare medium. So it would deviate away from the normal, and at one point what will happen is it would suffer TIR, because if I greater than IC critical angle, I'll suffer TIR. So I'll curve like this, which means my eye over here will think that this is coming from somewhere here, which means my eye would perceive the ship to coming from sky, not coming from below but coming from sky. And this is also an optical illusion. And this sort of an illusion, that ship is coming from the sky, not from below the horizon. This is your horizon, right? Not from below the horizon but from the sky, is known as looming. See, looming and mirage or mirage are essentially the same thing but in inverted fashion, right? They follow the same logic. Now this looming, this diagram of looming is also equally applicable in one more atmospheric phenomena, that is early sunrise and delayed sunset. Let's see how. This is a horizon, right? Again the same diagram. This is cold, this is warm. So if you have a sun over here, rays would try to come like this and gradually bend away from the normal, and it would suffer TIR at one point. And this diagram is not proper obviously, but yeah, just understand that it is suffering TIR, and similar sort of thing is happening over here. So you see your sun over here. So this is early sunrise. Why? Because my sun is below horizon. This is your horizon. Sun is below the horizon, so it's not actual sunrise. But you can see the sun much before the actual sunrise. Why? Because of total internal reflection. And this situation is known as early sunrise. Early sunrise. In a similar fashion, this thing called delayed sunset. Why? Even if the sun has gone below the horizon, the same thing would happen. You would feel that sun is still there above the horizon. So that would all, the same diagram can be thought of for delayed sunset too. Delayed sunset. So delayed sunset, delayed and early sunrise and looming have a very similar sort of a diagram, and this similar to mirage too, and all of these things follow the same thing of TIR, total internal reflection, when I greater than IC, and this is always in the case of from optically denser to optically rarer medium, which means from a higher mu to a lower mu. It bends away from the normal and gradually refraction goes away, so reflection takes place. Now, this also forms the basis for another atmospheric phenomena known as rainbow. But we will come to rainbow after we study something known as dispersion of white light. So in the next video, we'll be dealing with dispersion of white light, and we'll see what exactly white light is.